So continuing on to inverse functions. So the reason that we did the one-to-one, is it a one-to-one function, is due to the fact that when we're studying inverse functions, then an inverse function is only going to exist if it is a one-to-one function. So an inverse function at its most basic level is the opposite operation. So if you have a function which say would be something like x plus 3. Okay, so we have a function, say x plus 3. The function that you're performing on x is you are adding 3 to it. So therefore, the inverse operation of adding 3 is going to be to subtract 3. So therefore, the inverse function of x plus 3, the opposite operation would be to take away 3. Okay, so the original function is to add 3, the inverse function will be to take away 3. Okay, and that's what an inverse function is. So another example of that, if we say another function, simple function, so f of x would be 2x. So the function that we're performing on x here is we're multiplying it by 2. So think about what the opposite, the reverse operation is for timesing. So instead of multiplying by 2, if you did the reverse operation, the opposite of timesing by 2 is going to be to divide by 2. So therefore the inverse function would be x divided by 2. Alright. Another one perhaps, if we said that g of x was equal to, say, the cube root of x. So then what we're doing is just work out what the inverse function is going to be. We think about, well, what is the reverse operation of taking the cube root of something? And the reverse operation would be to cube it. Okay, so if we have the original function is the cube root of x, its inverse function would be x cubed. Alright, so if we're timesing by 2, the opposite operation dividing by 2, that's what an inverse function is. Alright, so these 3 examples that I gave you here are quite straightforward. If the function is more complex, then it'd be more difficult to find out what all the reverse operations would be. So the way that you actually find out the inverse is to do this. So if we just think about this function here, okay, so we should pick up now that f of x is just another way of saying y. So if we say instead of f of x is this, y equals x plus 3. So this is how you'd actually find the inverse. Now we know what the inverse is. We know that the inverse of here is x take away 3 because the opposite of adding 3 is to take away 3. So we already know the answer, but this is how you would get the answer. So what we do is we swap x and y around. Okay, so if we swap x and y around, this is a way of rearranging it so we get the inverse function. So once we swap x and y, then basically what you want to do is you want to make y the subject. So if we want what y is, y would be x minus 3, you see. And that is what we thought the inverse function was going to be. Alright, and that'll work with all functions, how to work out what the inverse function is. So again, in the second example that we did here, we've got y equals 2x. So to find the inverse, the trick for doing it is to interchange x and y, like so, and then make y the subject. So if I want to make y the subject here, you see, y is going to be, you divide both sides by 2, and then that's what we got when we did the inverse. Okay, so that's at the most basic level. This is how you find it. So for more complex examples, this is how you get the inverse. So when you do the reverse operation, the way that you do that is by interchanging x and y, and then making y the subject. All right. Other interesting information that we've got for inverses here, if we just looked at this quickly, if we look at what the gradient is. Okay, so we have a linear function here, right? So what is the gradient of this first linear function? So the gradient we can see here is 1. If we then look at the gradient of the inverse function, the gradient of this inverse function is also 1. Okay. Now, if we look at our second linear example here, and we look at what's the gradient of this linear function? So if we have y equals 2x, you see the gradient is going to be 2. If we have y equals a half x here, which it is x over 2 a half x, then the gradient of its inverse would be a half. So from these examples, we can see that what you can actually have here is when you times the gradient of f times the gradient of the inverse, it's always going to equal positive 1. Okay, because in this case you see 1 times 1 is going to give me 1. Again here, if we do the gradient of the function times the gradient of its inverse, in this case here, this is going to be 2 times 1/2, which again gives us plus 1. So this is something that in Unit 3 and 4 will be more important, and it's came up multiple choice a few times that you've got to understand that the gradient of the function and the gradient of its inverse, when you multiply them together, always gives you 1. Alright, so let's just get a few rules down here, okay, a bit of information. So when we're talking about an inverse, so firstly, as I said before, so for a function to have an inverse, well, for a function to have an inverse function, you can have inverse relations, but we are looking at inverse functions. So for a function to have an inverse, then it has to be a 1-to-1 function. Okay, it must be 1-to-1. Yes, it must be a 1-to-1 function. Alright, so only 1-to-1 functions will have inverses. Okay. So that's the first piece of information that we've got here. Second piece is how to actually work out the inverse. So what we're going to do is we're going to swap x and y, here interchange x and y, and then make y the subject. Okay. Okay, so by make y the subject, I mean that you're going to rearrange it so that y equals, and then it'll be in terms of x. Now, the definition in inverse is it's a reverse process operation. So the way that we get that is we swap the x and the y. So what we need to think about in methods is, well, what are the x values? So you should have an understanding now that the x values are always the domain, and the y values, they're the range of the function. Okay, so all the x values are the domain, the y values are the range. So if the definition of an inverse function, how we find an inverse function is we swap the x and the y values around, then it should make sense that the domain and the range are then going to swap. So your domain of your original function, okay, because that's your x values on your original function, will become the range of your inverse function. Okay, because that's what happens when you swap the x and the y. So if you swap x and y, then you basically, the x and the y, the domain and the range will interchange also. And that also means that when you have the range of your original function, that is going to be equal to the domain of your inverse function. Okay, so this is very important, that the domain and the range swap, okay, from the function to the inverse function. Okay. Alright, so if we think about another piece of information, I'll just give you this now. As we do examples after this, then it's going to make much more sense, okay, and I'll show you a few examples. A function and its inverse will always intersect in the line y equals x. Okay, so they will always intersect on the line y equals x, and I'll explain that in a moment. Alright, so that's just the theory behind it. Again, what we looked at before, which we won't go into too much this year, but the gradient of f times the gradient of the inverse is always going to equal plus 1. Which we seen when we did the linear functions earlier though. Alright, so let's just look at a few coordinates here. Okay, so if I just list some coordinates that we've got on our function, and then this is the notation for our inverse function. Okay, so f to the minus 1. And just make up a little table here. So let's just consider some coordinates. So if we start off here, we start off with a coordinate 5, 2. Okay, so on the original function we have the coordinate 5, 2. Therefore, what we're going to do here is you swap the x and the y. So that means that on the inverse function, it means that you can say you're going to have the coordinate 2, 5. If we have another point here, say minus 7, 0, you're then going to interchange x and y for the inverse. So that means that we know the coordinate 0 minus 7 is going to therefore lie on your inverse function. Okay, and any points like that. Okay, so if you've got minus 2, minus 5, on my inverse function, you're going to interchange, swap the x and the y, and we know that we're going to have that coordinate. Now this just doesn't mean for coordinates, it also means for asymptote. So say if you had an asymptote, okay, so say we had an asymptote at x equals 5, say. It means that on your inverse function, you say, you would also have an asymptote. But your asymptote on your inverse function, because we swap the x and the y, your asymptote would be at y equals 5. So in the original function, if you have a vertical asymptote, x equals 5, on the inverse, we know that we're going to have a horizontal asymptote, y equals 5. Okay, and the other way around, if you've got y equals negative 7, you're going to have an asymptote at x equals negative 7. So a horizontal asymptote on your original function will become a vertical asymptote on your inverse. Okay. Alright, so let's just look at this graphically, these points then, and we'll get a little bit of understanding of how this works. So if we just look at our Cartesian plane here. Alright, and then I've got the point minus 2, 3. So say I'm going minus 2, okay, maybe I just move this down a little bit. Okay, so minus 2, 3, say here. Okay, we got the point minus 2, 3. So think about what that coordinate's going to be. So this is the coordinate we have on the original function. So what would the corresponding coordinate be in the inverse function? So what would happen, you see, is if we've got minus 2, 3, that point's actually going to become 3 minus 2. 1, 2, 3, minus 2. Okay, so we know that we're going to have this point here. So this point here is going to be on your inverse. Say if we had the point here, say 1, 3. Okay, so 1 along and 3 up. Okay, so say something like this. Okay. Where would that point be on your inverse function? Well, because we swap the x and the y to find the inverse, then if we have 1, 3 on your original function, it should make sense that you're going to have 1, 2, 3, 1. That will be the point on your inverse function. Alright. So by using these coordinates here, we should be able to notice something interesting here, that if I actually put in a straight line here, okay, and I just look at this straight line, okay, that comes through this a little bit here, that comes through like this. Okay, so the straight line that I've put in here is the straight line. The equation of a straight line would be y equals x. All right. Now what actually happens when you have an inverse function, coordinates on a function and coordinates on a point, you see, is what the line y equals x will act as a mirror. So in actual fact, when we had this point 1, 3 here, it's actually reflected in this mirror y equals x to the point 3, 1. Also here, if you look at this point here, this is actually going to be reflected across the line y equals x. So this is what happens when you interchange x and y around. It actually causes a reflection in the line y equals x. Okay, so we've talked about reflections in the x-axis, reflections in the y-axis. So this is actually a reflection across y equals x. So if I took another point here and said that we had the point down here, say was minus 5, minus 5. So this is on your function. Where would this point be on your inverse function? Well, if we swap the x and the y around here, you see, then you're going to have minus 5, minus 5. So you see here, this point, because it lies in the line, because the x and the y value, because it lies in the line y equals x, then the coordinate's going to be shared by the function and its inverse. Okay. So this is important. This is why we had this last piece of information before, that we had the function and its inverse will intersect on the line y equals x. So this is the only point that the coordinates are the same in both the function and its inverse. So therefore, when we find the point of intersection, we always know that it's always going to lie in the line y equals x. Okay.